EC201, lecture 8. So to give you a quick recap of what happened yesterday, we basically discussed the characteristics of the MOSFET, more precisely the N-channel enhancement mode MOSFET, where the drain current in saturation is given by 1/2 mu n C ox W by L times VGS minus VT the whole square, where this equation is applicable when VDS is greater than or equal to VGS minus VT and when VGS itself is greater than some minimum voltage called the threshold voltage VT. And for an enhancement mode MOSFET, VT is positive. Alright. So continuing on, we basically wanted to make an amplifier. So we can now replace the two-port, the brick that we've been seeing so far, with the symbol of the transistor. And this is RL, this is RS, this is VS. So if this chap here is biased properly, that is, when I say biased properly, what do I mean? So in what region must this be operating when I say it's biased properly? The transistor is biased in saturation. Then the incremental gain, please note that this as is will not work. So now what is the operating point of the transistor? What defines the operating point of the transistor? When I say the operating point of a transistor, what do I mean? VGS and VDS. Okay, what is VGS? Please note that VS is a small signal source, okay? So what is the DC value of the voltage across the gate and the source? When we say operating point, what do we do to the signals? When I say operating point, what should I do to all the signal sources, the small signal sources? For any nonlinear network, when you're trying to find the operating point first, what would you do? Short out, so basically de-energize all the incremental sources. So all the incremental voltage sources will become short circuits and all the incremental current sources will become open circuits. Okay, so that means to find the operating point in this network, what would VS become? VS will become a short circuit, which means that the left end of RS is connected to ground. Okay, so what is the gate source voltage? Why is it 0 now? The gate current is 0, so the drop across RS is 0, so the VGS is 0. Alright, okay. So what about VDS now? I am asking you what the quiescent voltage VDS is. 0, and why is it so? And why is the drain current 0? The gate source voltage VGS is 0, which means that the drain current ID is 0, which means that the drop across RL is 0, which means the drain potential is 0 and the source potential is also ground, so VDS is equal to 0. So as such, if I just hook up a transistor like this, I can hardly expect to get any gain, but you could see that even before we started out, because there is no source of energy at all in this network, so you can't expect to get any gain at all. So in other words, this is good as an incremental circuit. If I somehow biased the transistor such that it was operating in saturation, then I could expect an incremental gain. If this transistor was biased in saturation, what would the incremental equivalent of the transistor be? So what is Y11? 0. Y12 is 0, Y21 is GM, and Y22 is 0. So if I have to replace the transistor with its incremental equivalent circuit, what would I do? For a general Y parameter network, this is Y11, this is Y12 V2, this is Y21 V1. So Y11 is 0, so what happens to this? Open circuit, so this goes away. What about Y12? Is 0. What happens to Y22? 0. And what is Y21? GM. So when I replace the transistor with its incremental equivalent circuit, this is what? So I have GM times V1 and this incremental equivalent for the transistor is only valid when the transistor is biased in saturation. And what is the gain? What is the incremental gain? VO by Vs? It is minus GM into RL, and this follows because V1 is the same as Vs. So if Vs changes, V1 will change the same way, and the incremental current flowing in the drain is GM times V1. So the voltage across RL is, the incremental voltage across RL is the incremental current times the resistance. The incremental current is GM times V1, which is the same as Vs. So the incremental voltage across the load is GM times Vs times RL. So V out by Vs is minus GM RL because the current is being drawn out of the resistor. Does this make sense? And sure enough, the incremental gain depends on the operating point. How does it depend on the operating point? The GM depends on the operating point. So the next job is now to figure out how to bias this transistor so that it is operating in saturation. So, in other words, we need to fix the operating point so that the voltages, terminal voltages are such that the transistor is operating in saturation. So, any suggestions on how I might be able to do that? What do we need? So, you have this transistor. I want to make sure that VDS is greater than or equal to VGS minus VT. Alright, so what could I do to bias? Okay, so this is the ID versus VGS curve, ID versus VDS curve for some value of VGS. So we choose some random VGS1 as our desired. You have to decide the operating point. I chose some value VGS1. Okay, and once I choose VGS1, the only thing to fix is VDS. So where on this curve would I want to fix the VDS? Towards somewhere here. This is the limit of the saturation region. So this value will be VGS1 minus VT, and so it makes sense to bias the transistor not so close to the edge of saturation. Why does it make sense that way? So please note that finally we are going to bias the transistor, then we are going to apply incremental input which rides over and above this bias voltage, thereby causing the drain potential also to fluctuate around the nominal. So there is a quiescent VDS, and because of the small signal applied between the gate and source, there will be a variation of the drain potential around the quiescent value, and eventually you want to get gain. So voltage swing at the output, which is many times the input value. So if you bias the transistor close to the edge of saturation, then there is a very real possibility that when the input signal is, small signal is increased a little bit, the transistor could get into the triode region. If possible, you would want to bias the transistor with a sufficiently large VDS, so that even when the input signal, small signal varies, the transistor is always sitting in the saturation region. And when the transistor is sitting in the saturation region, it behaves like a incremental. What kind of control source is this? This is an ideal voltage controlled current source. However, this is not a voltage controlled current source in the way you are used to in from the linear network classes. This is a voltage controlled current source which is only valid for incremental signals. So we chose some arbitrary value VGS1. We'll figure out what you must consider before fixing VGS1. You understand? To fix the operating point, you have to fix VGS1. We have to fix the gate source voltage and the drain source voltage. You have to fix VGS and VDS. And so let me choose some large value. So since I have put batteries of VGS1 and VDS1 between the gate source and drain source respectively, it's quite obvious that we'll be lying now on, this will be our operating point. And what is the current through this battery here? Which way direction does it flow? Upwards. And what is the value of the current? 1/2 mu n Cox times VGS1 minus VT the whole. And once a transistor is given, we know that the parameters mu n Cox W by L and VT are known. So ideally we would like to keep the transistor in saturation, so you would want to choose VDS1 to be as large as possible. Once I've fixed the operating point, the next thing is to add the incremental signal, and you finally want an incremental equivalent circuit which looks like this. The stuff enclosed in the green oval is basically the transistor operating in saturation. So the next thing to do is to add the source. I mean, the way we have biased it right now takes care of the green oval. Okay. So the next thing is to add the source and the load. Okay. So any suggestions on how I might be able to do that? Adding the source is basically straightforward. In principle, Rs, Vs. So now the quiescent voltage across the gate is what? What is the quiescent voltage across the gate? VGS1. The incremental voltage across the gate? Vs. Very good. And what is the total voltage across the gate? VGS plus VGS1. So the total signal across between the gate and the source is the quiescent value plus the incremental value. Great. So now what do I do to now I need to add the load. So what would I do? See, I want the incremental circuit in the drain to look like this. RL in series with VDS1. Does everybody see this? So if you go ahead, if you look at this diagram and say I want to form the incremental equivalent circuit, what do we get? VGS1 becomes, let's say we don't know anything, I just showed you the circuit and say find me the incremental equivalent circuit. What will I do? I will replace the MOS transistor with it. I will first find the operating point. Okay. And the operating point is given by VGS1. No, think carefully now. What is the correct? So the absolute potential at the drain is VDS1 minus ID into RL. So there is a small problem here because we wanted the drain source voltage to be VDS1 and we inserted the resistor in the drain in order to get the load, but now there is a DC drop across RL, which means what? Is VDS bigger than it was before or smaller than it was before? Smaller than before. So how do I fix this problem? One simple thing is to say I know what VDS1 I want, okay, and I know what VGS1 I want. So in principle I know ID. So and I know RL. So it's quite straightforward to go and figure out what this battery in the drain must be to ensure that after the drop across the resistor, the voltage across the drain and source is what I want. Quite straightforward. Okay. So instead of calling this VDS1, I will call this maybe VDD, and VDS1 is simply VDD minus, come on people, ID times RL. Very good. Okay, and ID itself is 1/2, and ID itself is 1/2 mu n C ox W by L times VGS1 minus VTD whole square. Does this make sense? So if I want to just find the operating point, in other words, given the circuit and to find the operating point, what I would do would be to de-energize all independent small signal sources. We derived the circuit starting from the incremental equivalent, and so when we take the circuit and go back to the incremental equivalent, we better get back the same thing. So let me just illustrate that. So you de-energize all this, small signal stuff. This goes away, okay, and that's all there is to it. And let's, for the time being, since anyway the gain doesn't depend on RS, let's just get rid of RS also, okay, for the time being. And this is the circuit which you use to find the operating point. And let me redraw this in a slightly different way. I have gotten rid of the battery and just put VDD. And it's understood that VDD is large enough so that VDS1, which is the drain source voltage of this MOSFET, is larger than VGS1 minus VT. Does this make sense? We need a battery for VDD. We also need a battery for VGS1, and that kind of seems like a little bit of a pain because you need two batteries. And what can you say about VDD versus VGS1? Which do you think will be greater? So we wanted to keep the transistor as much in saturation, as deep in the saturation region as possible. So it seems quite reasonable to assume that VDD is much larger than VGS1. So now, if you wanted to get VGS1, is there a way in which we can avoid the extra battery? To give you a simple example, you have a 5-volt battery, you want 3 volts. Will you go run to the store again and get a 3-volt battery, or can you do something smart with the 5-volt battery itself? One simple expedient is to simply use a voltage divider. So instead of VGS1, I will remove it, VDD, RL. So let me call this RA and RB. And what is VGS1 now? How will I choose RA and RB? We want VGS1 between the gate and the source, and we know that VGS1 is going to be lower than VDD. You only suggested that I put a resistor string, okay? So how will I choose the values RA and RB? So VDD times RB by RB plus RA should be equal to VGS1. So VDD is known, VGS1 is known because that's what we want in the first place. So is there a unique value of RA and RB? There are any number of combinations of RA and RB. Okay, so it's only the ratio that is fixed. The absolute values of RA and RB can be at this point anything. So this is one way in which you can set the operating point of the device to bias it, in a manner where it will remain in, it is in saturation. So given VDD, RA and RB, you will be able to get VGS1 From VGS1, you find ID. From ID, what do you do? When you say operating point, what do you understand? VGS and VDS. VGS1 is found already. The only job is to find VDS1. And how would I do that? VDD minus ID times. So this completes the biasing of the transistor to an operating point that we desire. Okay. The only, earlier we had two batteries. Now we have gotten rid of one of them and made life simpler. So the next job is to add the incremental source. Yes. Now how would we do this? Okay, one simple-minded idea, if I was a beginner, would be, I'd say, okay, why don't I connect the, okay, does this work? When I say does it work, what does it mean? We should be able to add the incremental input without disturbing the operating point. So now if I did this, why will VGS change? Great. So if I did this, please note that to find the operating point, I would have to de-energize Vs, which means that it's equivalent to connecting this fellow to ground. The operating point will now become, what will be the DC quiescent voltage across at the gate now? It's VDD times RB parallel RS divided by RB parallel RS plus RA, which is certainly not the same as VDD times RB by RB plus RA. Okay. And in the special case when RS is 0, what happens to VGS? The transistor is dead. You understand? So clearly adding the input just like that is not a viable strategy. Now, so when you have a problem, the first job is to figure out why the problem is happening and then see what we can do to fix the problem. Isn't it? Why was the problem happening in the first place? If I hook this up like this, the reason why the gate potential was changing was because DC current is flowing. When I de-energize this source, the small signal source, DC current is flowing through RS. You understand? And ideally all the current that flows through RA must flow through RB. But now some current is getting lost through RS. And why is current getting lost through RS? Okay, if I disconnected these two nodes, for example, what is the potential at node X? VGS1. Okay. What is the DC potential at, if you de-energize all the incremental sources, what is the potential at node Y? 0. Okay. So the reason why when I connect node X to node Y, the reason why current flows through RS is because the potentials are not the same. If you wanted, so turning the argument upside down, if I wanted no current to pass through RS, and why would I want no current to pass through RS? If no current passes through RS, then whatever current passes through RA will pass through RB, which means that the voltage at X will become VGS1, which is what you wanted, and that value is VDD times RB by RB plus RA. Is that clear? The problem is that the DC potential at Y is not the same as the DC potential at X. So what is the fix? If you make the DC potentials at X and Y the same, then no current would flow when you connect the two. So if I want to make the DC potential of Y the same as that at X, what do you think I must do? The simplest thing is to add so if you added a battery of value VGS1, then this potential is the same as this potential. So this potential Y dash is the same as the potential at X. And you see the way you solve the problem. You do something, you figure out, you see that it doesn't work, then you try to figure out why it doesn't work, then you add a fix. Hopefully the fix will solve the problem. In most cases the fix will add problems of its own, Then you have to go and fix those problems, and hopefully there is a convergent sequence, and eventually you end up with a working solution. This is how engineering works. Now, if I join y dash to x, then what do you think is the potential at x now? To find the operating point, what would you do? You would set Vs to 0, correct? And the potential at x will be, to find the operating point, what happens? So you have Rs, you have VGS1, similarly you have RA, RB and VDD, and by definition VDD times RB by RB plus RA is VGS1. You can see that no current flows in this direction, which means that this is equivalent to, this voltage is actually going to be equal to VGS1. And if you saw this circuit in the first place, it doesn't seem very obvious that that is the case, but since we've started from scratch and derived it, you know why it makes sense. You understand? Okay, so we've solved one problem, or we think we've solved one problem, but obviously I'm sure somebody is going to complain. So the whole idea in putting RA and RB was to avoid the battery. And now the question is, so clearly there must be a, let me tell you a couple of things about batteries. What is a battery? Or what is a voltage source? What is the job description of a voltage source? The potential between the two nodes must be the same regardless of the amount of current being drawn from the source. One observation is to note that a battery of value VB is completely indistinguishable from a capacitor's charge to value VB, provided what? A battery of value voltage VB is absolutely indistinguishable from a capacitor charged to the same voltage, provided no current is drawn from the, and by the same an extension of that argument, a battery of value VB is absolutely indistinguishable from an infinite capacitor charged to VB, regardless of whether current is being drawn or not from the capacitor. So you had, let's say, a huge capacitor charged to VB. If you draw current from the capacitor, that basically means you are removing charge from the capacitor. So the change in the potential across the plates of the capacitor is nothing but the amount of charge, the original voltage minus the amount of charge you have drawn from the capacitor divided by the value of the capacitance. So if the value of the capacitance is infinite, then the change in voltage is 0. So in other words, if you had an infinitely big capacitor, the change in it is absolutely indistinguishable from a battery, because whatever current you draw or pump into the capacitor, the voltage is not changing at all. You understand? Now, can somebody tell me a clever way of getting rid of VGS1? So you can replace this chap here by an infinite capacitor like this. And what is the voltage across the capacitor? So in steady state, after the capacitor is charged, this voltage X will be VGS1. The voltage on the left plate of the capacitor will be 0. So the voltage stored across the capacitor plates is simply VGS1. So in other words, it's completely, since the capacitor we postulate as being infinite, it is equivalent to a battery. Another way of looking at it is that the capacitor is an open circuit for DC, so it doesn't allow DC current to flow through it. So these two are very important observations. That is, a finite capacitor of value C when charged voltage VB is completely indistinguishable from a battery of the same voltage as long as the current being drawn from the capacitor is 0, and an infinite capacitor is absolutely indistinguishable from a battery. And so we've solved one problem. The next thing is, so what would be the incremental voltage at X and voltage at X? VGS1, okay. So how will you find the incremental voltage at X? What happens to the capacitor? The capacitor this is an infinite capacitor, so it is indistinguishable from a battery charged to VGS1. So for incremental signals, this infinite capacitor becomes a short circuit. To find the incremental voltage at X, what do? We have Vs, we have Rs, and the the capacitor becomes a short. What else happens? What happens to VDD in the incremental equivalent circuit? It's a voltage source, so it must become incrementally 0. There is RB to ground, there is RA to VDD, but in the incremental circuit this is also ground. So what is the incremental value at node X? It's Vs times RA parallel RB by RA parallel RB plus, right? And what is the absolute voltage at X? VGS1, which is VD times RB by RA plus RB, that's the quiescent value, plus so this is the quiescent value plus the incremental value, which is RA parallel RB by RA parallel RB plus RS times Vs. What is the drain potential? VDD minus IDRL. What is the incremental voltage at the drain? Okay, what is the incremental drain current in the transistor? In a transistor biased in the saturation region, the incremental drain current is given by what? Gm, which is the transconductance of the device, multiplied by the incremental what voltage? Gate source voltage. What is the incremental gate source voltage here? Alright, so the incremental drain current is nothing but Gm times Vx, and that incremental current flows through RL. So the incremental gain of the entire amplifier from the input to the output is, so let me draw the incremental circuit. This is Vs, Rs, RA parallel RB, which is the incremental Vx, and there is Gm times Vx, this is RL. And why is RL connected to ground on one side? The incremental equivalent circuit, VDD becomes ground. So this is the incremental output. So VO must be equal to minus Gm RL times Vx, which is minus Gm RL times RA parallel RB by RA parallel RB plus RS times, which means the incremental gain is minus Gm RL RA parallel RB by RA parallel RB plus RS. So please think and reflect about this over the weekend, and we'll continue on Tuesday.